up Unit 5. We're going to do simple harmonic motion, and we're going to do simple with a capital S. All right. Oops, let's make sure my pen works. Your physics teachers will cringe at this. Alrighty, but it warms us up for what you're going to see in your calculus classes and so on. So here we go. Simple harmonic motion is actually a pretty big deal in the world of physics and applied mathematics, where if anything is working in a wave, and that wave is fairly consistent, we can do a lot of cool mathematics. I know oceanographers and a whole bunch of other people do this. Your cell phone frequencies, lots and lots of things on this. So your physics teacher is probably going to show you something like this and go, yay, okay, that's a lot of fun. What is all this? Well, you got omega, and typically what happens is that, remember in our transformative form that I had C right here? Well, we're typically not shifting it right or left. We have a start time of 0 and a specific end time. There's not going to be any shifting right or left, so that C actually doesn't come into play too much. And we kept it simple on our course, calling B the omega, and A is still our amplitude, and so on. Okay, but it's going to be the same thing. Now, the other thing is that the problems we're going to be doing is something either going to start oscillating or we're going to drop it, like we're going to drop an object and it bounces up. When we start high, it's going to be cosine. When we start middle, it's going to be sine. Most of our examples are going to be cosine, however, okay? Because again, we're keeping it very, very straightforward. So let's go ahead and go on and just work some examples here. So when you read these, you want to get an idea of what's going on here. Something's pulled up, a weight's pulled up 16 feet off the ground, okay, and released at time 0. And then it's dropped and it goes down to 2 feet above. Then it returns to its initial position every 30 seconds. That sounds like a period to me. So let's go ahead and sketch this graph. And it could be an ugly graph. And with my writing tablet, it will be an ugly graph. But that is okay. So what we're going to have is we're going to have a high of 16 and a low of 2. And it's going to drop, bounce, yep, see, ugly graph, and it's going to stop right at 30 seconds, my period. All right? What we want to do is be able to write this into our function bx plus c plus d. All right, that's a b right there. Now, we're not going to need our c. We're not going to translate it left or right. So we want to figure out what these things are. First thing is we need to figure out what our amplitude is. Amplitude is high minus low divided by 2. Remember, amplitude is high minus low divided by 2. So that's just 16 minus 2 over 2, which is equal to 14 over 2, which is equal to 7. Okay? So our amplitude is 7. So guess what goes right there is 7. We're going to use cosine because we started high. We need to find what our B is. B is not our period. It's our angular frequency. So we're going to go ahead and set it up to the formula that B is equal to 2 pi over B. Period is equal to 2 pi over B. Well, if my period is 30 seconds, we're going to do 2 pi over B and solve for B. Multiply by B. 30B is equal to 2 pi. Now I'm going to divide, so B is equal to 2 pi over 30. All right? Cut that in half, and it's pi over 15. Got it. Now we just need how much we shifted up or down. There's a couple ways to do this. One, you can look at this and find your equilibrium. It's between 2 and 16. All right? It's like the midpoint. The other way to do that is D, there's a formula for it, is equal to amplitude plus low. All right? Or you could just kind of look at it and say, oh, there's my equilibrium. All right? How far did my equilibrium go up from 0? My amplitude is 7. My low is 2. So my D is 9. All right? So now we have everything we can do to write this equation. So my function is y is equal to my amplitude, which is 7, cosine. There's my angular frequency, pi over 14. So we're going to do that, pi over 15. Did I put 14? Silly me. Half of 30 is 15. All right, x and then plus 9. There you have it. That's all we're going to be doing. Your physics teachers, first of all, are going to cringe, but they're going to do something slightly different with this, okay? We're just warming you up to it. So let's do a couple more examples. And here we have a weight is supported by a spring. So I'd like to go ahead and start sketching. And again, it can be an ugly graph. We're 14 feet up. And it's going to drop at time 0 to a minimum height of 10 feet. So this is 10, this is 14. This is 10, and down here is 0. This is x time, and this is height, y. Okay? So we drop it, bounces back up, goes up again, and does the same thing over again, but this is going to be 5 seconds. You don't have to sketch the graph, but sometimes I find it rather useful. First things first, amplitude is high over low, high minus low over 2, high is 14, low is 10 over 2, and that's going to be 4 over 2, which is equal to 2. Okay, and again we start at high, so we know we're cosine. Period is 5 seconds, so we want to solve for b. b is equal to 2 pi. Well, I got ahead of myself. So we're going to solve for b. So we're going to have 5 is equal to 2 pi over b, multiplied by b on both sides. We have 5b is equal to 2 pi. Divide by b on both sides. Divide by 5. b is equal to 2 pi over 5. All right? Okay, so that gets you that. The next thing we need to do is how much did we translate it up? Again, you can find your equilibrium right here at 12. So we know we went up 12. But we can also do the formula of A plus low. Well, my amplitude is 2. My low is 10. So my D is 12. So we write our handy dandy little function of y is equal to amplitude of 2 cosine. Okay. So 2 cosine, I'm pretty sure it's 2 cosine. Here it is. There it is. 2 pi over 5. 2 pi for 5 of x plus 12. There we go. Okie dokie. Last one. And go ahead and pause and try and work this one on your own. This one's a little tricky. I'll get you started. So a buoy oscillates in the water. So we have an equilibrium, and it's going above and below that, a total of 4.5. Well, if you think logically about it, you're just splitting that 4.5 above and below your equilibrium. Call that 0. Y is equal to 0. Okay? So we're going to be 2.5 above. We're going to be 2.5 below. And it's going to oscillate down and up and down and up. Every 8 seconds is the period. I'm going to go down and up every 8 seconds. Okay? So 8 seconds it does that. Ugly graph. It's okay. So first of all, we know our equilibrium is 0. So our D is going to be 0. That's going to be pretty easy to do. But we need to find the amplitude. What is the amplitude? Well, we're 2.5 above our equilibrium. You can still do high minus low divided by 2. All right? And you're going to get 2.5. All right? But just looking at, you're going to be at 2.5. Our period is interesting. So our period is 4.5. No, wait a second. We're seconds. 8 seconds. All right? But our B is what's interesting. 2.5, 2 pi over B is equal to 8. Multiply by 8b on both sides, you get 8b is equal to 2 pi. Divide by 8, you get 2 pi over 8, which is equal to pi over 4. D is equal to 0, and let's just go ahead and write our function. Y is equal to cosine 2.5 of pi over 4 x. There you have it. That is keeping the capital S in simple harmonic motion. These do get quite a bit more complicated, but not for our purposes with online course. Okay, we're not going to make it any more complex than this. Alrighty, you should have paused and worked these problems. If not, go back on a blank sheet of paper, rework the problem, and then check them. Alrighty, see ya.